So this is just a few slides, which is from, I think, Professor Murthy's book, where he tries to show that if you add it's a low-rise building, but the concept is the same, that if you add a shear wall in anywhere, or a structural wall anywhere, how does it affect the dynamic response, and how does this affect the roof displacement? So, and the location. So basically the idea is to see that the symmetrical distribution gives us symmetrical response. So this one here, I will go back to the modal response. So right now you can just see the arrangement. On the periphery, we have big advantage. In the middle, we have less advantage. And then if you put a core, you also have a little bit less advantage from that. So depending upon where you put the walls, it is very important. So layout of the walls, structural walls in the frame shear wall system is very important. And this controls the displacement, the modal response, and the everything. So we will, when we do the project, then this is an area where you should look into how to arrange the walls and frame in your building. Because, and you can read this slide. There's nothing much to explain here. Okay. So he studied various locations. Easily you can see it's an interesting observation. And then he found that this is most efficient in this direction and so on. Okay. So now shear wall frame coupled. So we can put the frame, and then we can put some of them, some of the frames can be converted into walls. And this is a very important observation, because not only we can put the walls and then couple them with the frame, you can also put the walls inside the frame. And sometimes these are, we can call them partition walls, or they are not as thick or as as big as typical shear walls. So the frames, when you put it there, then the columns on the outside and the beam, they sort of frame the wall, and the wall inside becomes like a bracing. And I will discuss this in a few minutes. But this is quite useful in buildings where the partition walls can be converted into structural walls. Okay? So that we can either we can use the partition walls as structural walls, or you can convert the partition walls into structural walls. This is especially true for low-rise buildings, where masonry walls are used and they have a lot of stiffness. And so they need to be included in the analysis, and they interact with the frame and alter the frame response. So this is important. The walls may have a positive effect on the performance, or may have a negative effect on the performance. And it depends on the relative stiffness and strength and ductility of the frame and the wall. Okay. So if the walls are, you start with the wall very stiff, it will attract a lot of force. And if it doesn't have the strength and the ductility, it will break, and then the force will go back to the frame. So a very, sort of delicate balance has to be created if you decide to go this way, because the two systems are mixed. But if you are separate frame and shear wall and separate and just coupled, then it's easy to manage their response. Okay, so now we come to this one, the main topic of today. So last time I showed you the buildings with the outrigger and belts and trusses and so on, and many buildings, especially this is a very nice building in Wuhan, which shows that concept. So outside, what you see is a belt truss. What you see inside are the outriggers. So they have several belt trusses running all the way on the building frame. This is a very efficient system for especially a tall building like this. So I want to go into more detail about what are the outriggers, what are the belts, what are the real outriggers, what are the virtual outriggers, what are the flag walls. So there are 5-6 concepts that we will discuss today. To me, this is one of the most important concept for the kind of buildings that you will be hopefully designing, 200, 250, 250 meter range. This is most important. So let's go into the detail of this one. So outrigger and belt systems are basically that they will try to utilize the core wall as the spine, and they will try to extend the arms to the outside column on the boundary. So it's an internal system, and they will try to strengthen each other from that, because the outer columns are very far. They're not connected directly. So how do you follow the 4 commandments? That's the idea, to connect the outer frame with the core walls, and then through that connect to the other side. So actually one side of the frame goes to the core wall, flows through and goes to the other side. So the whole system, outer two columns, boundaries are connected to each other through the outriggers and through the core wall. So that's the idea. So this is just, you can read this one. So that's we have already seen this slide, and I mentioned to you that this is the core wall. So these are the extended arms, and then you put the columns outside. So basically these are like sticks, outside, you can just balance yourself. And then the stiffness and everything will depend on the stiffness of these arms. And these arms are the outriggers. So trying to make these arms as stiff as possible is of course very good. But the problem is that they will block the building's interior because people have to walk through. So if you put these solid walls, then how will people go from one side of that side of the building to this side, because you block the whole floor? And normally it's not just one floor. They can be 2, 3, 4 floors high, depending upon the building. So they have to be very stiff depending upon the distance. So depending upon this distance from here to here, this can be very tall, very high. One floor may not be enough, maybe 2 floors, maybe 3 floors. So if you do that, you basically block many floors from using. Most commonly, they are used where we call the service floors. So every tall building, especially hotel or office, they have a service floor where they put all of these services like the generators, the air conditioning systems, the electrical systems. So they normally, those people take one floor away and they put all the services there. And more normally it's in the middle, so they can service the floors below and service the floors above. And we normally go back and request the mechanical engineers, can we use your floor to put these outriggers? Because your pipes can go through, but we mostly utilize those service floors to put these outriggers if they are big enough. And there's so many alternatives, and today we will discuss all of them. But the concept is this one. So now I want to show you this very important observation, the difference between frame, truss, and wall. So that is the frame, the first one. So you can see there's a lot of displacement here from here to here for nearly the same force. And if you cross and put a truss inside, brace it, you get very small displacement. And if you use a wall, you also get very small displacement. These two are almost the same. So this you should keep in mind, that wherever we are talking about a wall or an outrigger, concrete solid, it also means truss. So you can always replace a truss by a wall or wall by a truss. So that's why when we call belts or outriggers, it also means outrigger trusses or belt walls or belt trusses. So please do not get confused that they are two different things. It's just a way to put them there. Both of them have very similar behavior and very, very similar capacity. So you can either choose to use a truss or you can choose a deep beam. Both of them will work almost the same way, and they basically block these panels from shear deformation. So this is a shear deformation, as you can see here, and this is a bending deformation. So they convert the shear deformation into a bending deformation. And that is the key strength of this one. So they have a lot of bending capacity, and then in return, they give you a lot of shear capacity. Okay, so this is an example that is the same thing, outrigger effect, but instead of wall, they put the truss, but the same thing. And this is very, very important for you to see how these columns, one column goes up, one column goes down at the end of this. And this is the key to gain the strength or gain the advantage, because we are converting the bending into axial shortening and axial extension. And that normally, in general, every member has a very large axial stiffness and small bending stiffness and small shear stiffness. So if you can convert the bending moments or the shear forces into axial forces, then you suddenly increase the stiffness substantially. Like in this one here also, here we converted the bending or the deformation here into axial deformation of the frames. And that's how we got the advantage and increased the stiffness. So that's what you can do here also. And so this effect is the key for the interaction, that you are actually preventing the top level is no longer straight. And this effect is going to push pull this column up, push this column down. One is going to be in compression, one is going to be in tension, and that tension compression couple provides us the stability. We can also move this to the top like that, and the same thing happens. So this one comes in compression, this one in tension. The whole building becomes stabilized if you move and this is called a cap normally, or a hat truss or a cap truss, top of the building. Many people use it. This is a shear wall internally, but both of them. So shear wall is doing like this, and you add an outrigger to that to prevent from this one from happening. You basically enforce this compatibility. So this is the way that we use the core wall, which is already converted into a shear deformation mode, a shear system, and then we add another one on top, and then the columns just become sticks. So it just becomes columns become just sticks, beams become irrelevant, and the whole system works as a wall, outrigger, and columns supporting as axial forces. Okay. So we can see from here the effect. So this is a wall, beams only. We put one at the top, we put one in the middle. This is a small building, but just to show the concept. So now if you see the response for this one, you will see, the same thing, cap wall and shear wall. We can put it at the top. It looks something like this, just to give you an idea. Let's move on. So if you do that, when you displace it, you can see here that this one is displacing that much. Quite large. This displacement is much less. This displacement is even less, right? So you can see from here, this displacement is only here, and this one is a little bit more, and this is very, very large. So that means as soon as we put the cap on the column, on the frame, the displacements were controlled, the drift was controlled. When we put it in the middle, it was much better. Okay, why the one in the middle is more effective than the one at the top? Because the axial only in this case, only this much length is subjected to axial shortening and elongation. So if the same column size, the stiffness is EA over L, right? The L is the main parameter. So when you divide the long length, the stiffness becomes shorter. And when you divide by the shorter length, because the columns above are not participating in the outrigger effect, only the columns below are participating, and they are shorter in length. So simple question, EA over L is the stiffness. So if the L is shorter, the stiffness will be longer, will be larger. So it becomes large. So that's exactly the right. And this is an important note because you can play with this thing when optimizing the location of the outriggers. So you can see from here that this is the axial force, and you can see only the axial force below the outrigger is increased. Above that is not affected. And this is the outrigger is causing the compression force in the entire column, all the length. So the shortening will be more. So the stiffness will be smaller. So more rotation will occur. Okay. So that's the, and you can see, so this idea that below the outriggers, you get this very large force is the key to the behavior. So now what we can do is to optimize the structure, we can increase the column size here further and reduce the column size above. So it will also be economical because we don't need the column above to be so big. So these columns are normally becoming larger, which are at the end of the outrigger. Okay. So that's the axial force thing. And then the wall stresses, you can see the wall stresses also change, not much, but there's a local effect of that, but that's not the critical thing. And this is the moment in the beams. So you can see here, all the beams are taking a lot of moment. And this is the key. Last time I told you, what is the key on having this coupling effect? If you cannot increase the size of the beam because nobody will allow, the architects will not allow you, you cheat it by putting them all together at one place. So you can reduce the depth of the beam on every floor and add them all up into this one. But the interesting thing is, once again, 1 + 1 not equal to 2. Okay. See this carefully. This is one beam. Let's say it is 600 millimeter and another beam 600 millimeter. So if this has a I equal to whatever, This is also I equal to I1, correct? BDL squared, yeah, right? You add them together, it will be I1 into 2. If you just have two beams, one here, correct? Multiple beams, if you add them together, you just add their stiffnesses, correct? But if you have a beam which is actually 1200 by whatever, the stiffness of that will be not 1 plus 1, it will be 4 times. So suddenly you increase the stiffness by an order of magnitude, 2 orders of magnitude, by putting them together at one place as an outrigger rather than distributing them on many floors. So that's what we do. We use engineering to beat the math. Like I told you, we take out the thickness from each of the beam and we put a big beam and we get a much better effect, cost saving also, because we save on every floor. That's why it is possible to have flat slab at each floor level. We don't need the beam anymore, and we put all the beams together at the outrigger. And that is the reason why the flat slab system with wall, with outrigger will work. Otherwise, it cannot work. That's exactly the way that we do that. We collect all the beams together, small beams, and make them a big beam and put them as an outrigger. Maybe 2 floors high. Imagine 2 floor high beam, 3 meter plus 3 meters, 6, 7 meter. 7 meter high beam. This is 3.2 meters. 7 meter high beam, imagine the stiffness of that thing. So that's how we will use that concept to put, and then you can see the beam, the moment in all the beams is reduced. So we get a lot of economy by getting down, getting rid of moments in all the beam, economizing the reinforcement. In fact, getting rid of the beams altogether, having a flat slab, and put it all in the outrigger. So that's how important the outrigger is. And shear force also. So you can see here a lot of shear force in the beams here, lesser shear force, much less shear force here. So we reduce everything. We reduce bending moment in the beam, we reduce shear force in the beams, we reduce the deflection, we reduce the drift. It's just good all over, right? So one simple concept of putting the outrigger solves most of your problems in the tall building: drift, deformation, large beam problem, large bending moment, whatever. The only problem is architects hate it because they will not allow you to do this. And though engineers have been coming up with alternate ways to do the same thing without affecting the flow. Okay. The concept is good, but the problem is implementation. Okay, so outriggers reduce everything. So many R's there. So they reduce the natural period, good for good response, reduce top displacement, reduce drift, reduce moment and shear walls, and most importantly, they reduce the moment and shear wall also, not only in the beams, because the axial forces take the moment away from the shear wall. So you save on the shear wall moment a lot. It followed all 4 commandments that we talked about, and then the only thing it doesn't reduce is shear in the shear wall. That there's no way for you to go around that, because we are converting the moment into axial, but the horizontal shear will still remain. So shear walls will now still need to be designed for the shear, but not so much for the bending. Okay. So this is, and then need space to implement. That's the problem. That's the challenge. So this is kind of summary of the outrigger, use of the outriggers. And sometimes we can replace the outriggers by trusses, as I mentioned to you, by 2 floor of truss, 1 in tension, 1 in compression. So when you do that, it becomes a truss, always 1 in tension, 1 in compression in each direction. So this is a very common configuration. Instead of using a solid wall to connect, we put diagonal strut members so people can walk. So you can put the door underneath that because it's high enough, so people can still move around those diagonals, and you don't block the rooms. You can still put the door there. Okay, so that's the advantage of using a truss rather than a wall as an outrigger. And then we can replace these trusses because trusses are not good for seismic, The bracing are not good for seismic. First of all, please remember, bracings are never good for seismic response. Why is that? Why I keep making this statement that braces are never good for seismic response? Once again, I mentioned to you the way for wind, braces are excellent because we keep the wind within elastic range. So you can design the braces to be within the elastic range. Forces are controlled, so the buckling can be controlled. But in seismic demand, we are expecting a nonlinear drop of 3-4 times, and buckling and the braces have no such capability to give you that drop. For the moment, it is a moment hinge. They will yield, but bucklings don't. The normal braces do not yield. So they will attract a lot of force, and because the force is about 4 or 5 times the design capacity, they will just buckle, and then it will be a problem. So then BRB. So we normally, if we are going to use outriggers, they have to be BRB. In seismic zone. In wind zones, no worries. You can use it. So if it's a seismic zone, then you put the braces, but not ordinary braces, BRBs. We actually designed the first BRB tall building in Philippines. It was quite interesting. And then we went to the site, take a look at that. It looks nice. Huge BRBs, imported from US. Very, very large members. Now let's look at the location of the outrigger. So don't worry about the truss. This is just the same. Like I told you, could be wall, could be truss, doesn't matter. So deflection, if you put it over there, this is the deflection with outrigger. This is deflection, free deflection. So you get that deflection. Okay? So you get reduced deflection, reduced drift. And this is the moment in the wall. So you get, this is the moment without the outrigger. This is the moment with the outrigger. So you reduce the bending moment in the wall and you reduce the deflection. This is the typical effect of putting the outrigger, as I mentioned to you. Okay? Now, if you move it down, you get that further reduction at the top and the moment like this, like that. The only problem is that the moment is only reduced below the outrigger, not above the outrigger. So you divide the wall into 2 parts. Okay. But the deflection is now becoming much and much less as you start to move down. So it's like at the top is not so effective. As you go down, starts to become effective. When you go down too low, starts to be ineffective again. Yeah, because most of the building is above the outrigger, so you don't get the advantage. So there is a sweet spot somewhere. Okay? And this is where you're talking about. They study all of that, and then finally they find this sweet spot somewhere here. This is the one, right? So this is about 1/3 from the top or 2/3 of the height or something like that. Depends on the building configuration. It's not universal law because it will depend on what the size of the wall, size of the core and everything. But if you're doing a project with outriggers, we should do this study. Find out what is the best location of the outrigger, which gives the best benefit, and then try to fight with the architects or with the people to get you that. Sometimes they will tell you, oh, you can only take floor number 42. Okay, then you have no choice. Okay. But if you have a choice, you should do a study to find out what is the best location for the outrigger and the belt. We will talk about the belt in a minute. Then how many outriggers? That's the next question. Because you don't have to put one. If the building is very tall, I showed you the China building. There's seven outriggers, 6 outriggers. How many outriggers you should put? That's the next question. And once again, it's a parametric study. You can put 1, 2, 3, depending upon, if you only get 1 floor at a time, you have to put many. If you get a big space for 3 floors, maybe you can go away with 1. So it all depends how the tall building is, how many floors are available, what height is available. So within those constraints, you have to try to find out the best solution of the number of floors that you will use for the outrigger, the number of outriggers that you will place, and the location where you will place, and the thickness and many things. So you play around with all of that to find the best solution. Okay. So this is a very now interesting thing coming up. Real versus virtual outriggers, like virtual classroom, or virtual, it doesn't exist, but it has the same effect as an outrigger. And this is somebody found from, I think, over Europe a few years back. They found this effect that you can get the outrigger effect without making an outrigger. And that's called virtual outrigger. The architects absolutely loved it because now you have an outrigger which is invisible. So how does that work? So basically, this is the real outrigger here between the wall and the outer column. But if you just move them to the outside instead of the middle, that means they are no longer blocking the space in the building. They just been moved to outside wall. They're still there, but not at the location where we normally put them to connect the wall and the column, like I showed you earlier. They are now moved away on the boundary of the building, and now they're called virtual outriggers. They're virtual because they are not present inside. They are somewhere, and you may not see them, you may see them, depending upon what it is. But basically, the room is clear now. So why do they work? Who will explain that to me? Why do the virtual outriggers still work? Structural mechanics stuff. Yeah, that's in concept, you're right, but why is it working? I know, I mean, you're saying is correct, it's stiff and all of that stuff, but how come we move them away from the wall and they still worked? Diaphragm effect. So the thing is that the two floors are very rigid in plane. So whether they are blocked at the wall level or they're blocked anywhere, the whole floor is now unable to have shear deformation. So it becomes a solid block. So whether the outriggers are directly connected between the wall or they are just blocking that whole floor from deforming. So the whole floor becomes a solid, big block, right? Like a box. So it's a box effect. So box, you have side, you put those walls of the box on the outside, the box still becomes rigid, right? Wherever you put those dividers. So the two floors and this wall, they can convert that into a box, which is rigid. And once it becomes a rigid box, then it doesn't matter where it is located. Of course, it is not as effective because there is some shear flow between that, and then there's some deformation in the plane of load. You have to make the floor thicker to make sure that they work like a box. But the good point is that you can move these outriggers outside of the view and then convert them into those. Now, in this direction, you need them here, but in this direction, you need them there. You need them in both directions, not only in one direction. Because in each direction, for this direction, these walls will be fine. In this direction movement, you need to put them outside. So basically, they become like a belt because they are like a belt around the building. And that's where the belt concept came up, that if you put the virtual outriggers on both directions, they form the belt around the building. And that completely makes that floor, 2 floors or 3 floors, as solid boxes. And they're just then connected in the middle to the wall. So they work perfectly as a solid, rigid block and restraining this, getting the same effect. So the belt concept came up. But when the people have the belt, they also found some other advantages of this belt. The other advantage is that when you put the outriggers only here, these 2 columns or these 4 columns are the one which are carrying the axial compression. So that which means that these 4 columns will get very large forces compared to other 2 columns which will get very small forces. Which means that you have to make these columns very big. Which means that architecturally it's a problem because architects don't want to see 2 columns very big and 2 columns very small. Another, if you don't do that, you have a big problem because the differential shortening will happen. Some columns will shorten more and some will shorten less because the forces are so much different. So you end up with the problems anyway. Either you match the size of the column with the axial force, or you put the more reinforcement, but the deformation cannot be controlled by more reinforcement. So which means that when you put this belt here, it also distributes the force to all the columns equally because of its stiffness in that direction. So the belt is very effective both as a virtual outrigger, but also very effective in distributing the force to all the columns underneath that, because now if you have another belt here, then all 4 columns will get the same force because this is very stiff in the direction. So the blocks becomes very stiff, and all the columns below that become equally effective, increasing the stiffness because now every column is helping in the axial deformation. So the system becomes extremely nice. So since this discovery, almost all tall buildings are now outrigger belt systems. You don't have many buildings without the belt because belt is so effective. both this way and also in this way. All right. So that's where the outrigger belt system comes up. So that's how it works. So we have a core wall, and within the floor, this is the system. This is the belt outside. So we have the lateral load. Everything goes through shear and then through bending. There's a whole forces going through the two floors. So the two floors become part of the system. So the force transfers through the slab from the core wall to the outrigger in plane through the slabs. So those slabs may have to be made thicker to handle these additional in-plane forces. So that's another thing that people use. Sometimes they in some buildings you will see that they bring the columns up to this one, and then they just remove the columns and then transfer them to mega columns, which we will talk about. Another concept, completely change the system to not have the columns in the middle participate at all, right? Yeah. So just have a belt resting on the outer four columns, remove everything else. So make it very, very simple. So that's the idea of the whole concept of belt wall system. Belt, wall, outrigger, virtual, real, everything is combined. So people can use all kinds of things now. You can make trusses, you can make outer trusses, you can make walls, you can put VRB, you can have the freedom to do all kinds of combinations. So adding the belt, so now this belt is added all around. So all the columns now in the floor below, this solid floor will make sure that this is a rigid floor, but belt will only work if there's a core. If there's no core wall, it won't work, because core wall is the one which is actually helping us to do all of that outrigger effect. Okay. So we need that core wall through which the whole system is connected. So this is the final virtual outrigger with belt acting both as a belt and outrigger here. Sometimes you can put outriggers also and a belt together, depending upon availability. Sometimes you can combine trusses with walls, with all that. All options have been used. So this one here, belt wall system, you can put at the top 2 floors, or you can put it here. That is a frame without anything. So this is how the outriggers inside will work, and that is the belts outside that will work, right? So that's actually one of the theses going on, the two theses going on this semester about outriggers and belt wall systems, trying to compare which one, how do they work, and which one is better. And this is, once again, different configuration. This is core wall alone. This is the outriggers, outriggers going in 2 locations, belt wall alone, then outrigger and belt wall together. So you can study all the possibilities. This is all research kind of a thing, right? So students who are working on it, try all these options. Start with the bare frame, then we add the outriggers, then they add only the belt, then they combine them together, then they move them around, study all this stuff. Okay? So it's interesting. But the end, once you do that, then you have to do the nonlinear dynamic analysis for the real ground motions to find the real response. It's not enough to just do elastic design. The real is, how does it really work in the end? So this is a good example of how that works. So now you can see here, this is another example now coming to, so you have a belt. These small columns are not doing anything. They're just carrying nothing. The outer belt is truss resting on these green columns. And then the purple are the outrigger trusses connecting to the core. So you have this system. You have this sometimes the belt walls, the outrigger walls are with openings. So we say, okay, we have a wall, but we will give you the door to pass through, small door, right? Compromise. So there's an opening there. We stagger the openings, so it's not at the same location. So many things have been done, and this leads to another new system called flag wall, which I will discuss with you later. So as long as we can keep the concept, we have to compromise on the availability of space and maybe give some openings here and there, and then study how it works, right? So this is a good example of where outrigger walls are there with openings on every floor, but staggered, not at the same location, because that will weaken the whole thing. So you staggered them, that one floor is here, another floor is there. And then you can put those trusses, so you can see here, and then you can put these things here and there and there. So this is the concept of the outrigger. Another one, buildings, same thing here, outrigger, perimeter truss. So you can see here very clearly outriggers, belts on these buildings. belts here. You can see this here, trusses, belts. So you can see in many buildings, these existing now. If you go around, you can actually observe them. Maybe you didn't notice before, but now you will start looking at. Unfortunately, you cannot look at any tall building without now looking at what's going on, right? So this is once again the same thing, outrigger. This is actually, this diagram is made by one of your senior students. He's now doing PhD using BIM. So this is the outrigger with openings. So you see this wall with the openings there. This is the outrigger belt with the bracing there. You can use that one, belt truss. And then these are the outriggers inside, then only the outriggers there, and then the belt. So he converted my diagrams into 3D nice figures. So virtual outrigger and then belt. You can see here and over there, another one. This is the outriggers in this building. You can clearly see outriggers going all the way. So many outriggers there. Normally, you may not have noticed that those are the outriggers, which doesn't have opening, doesn't have windows, right? Look like an architectural nice design, but actually they are very much structural. So this is the BRB, which can replace the braces, and this can also be used as outrigger and also as a damper. And so we will talk about this when we go to seismic design and seismic evaluation. Okay? So BRB basically is a very interesting device. It's a very simple concept. And one wonders why it takes so long to come up with some simple things like this. It's so obvious. So what they do is that the outside core is larger in size, and that prevents it from buckling. But inside is a smaller section which can move in and out freely without yielding, without buckling, and the outer core prevents it from buckling. So you separate the buckling capacity from the axial capacity, because normally if you have a concrete member, the buckling capacity is related to the size of the member, and the strength is also related to the size of the member. So you cannot separate them. So if you increase the size for the strength, the buckling capacity will increase, but the stiffness will increase, which is not good. It will attract more forces. So you cannot find the good combination of strength and buckling for a long brace. But here we separate the two together. We separate the strength and ductility into the core, and we put the casing as a buckling prevention. So the real member is inside. Outside is just a casing preventing that member from buckling while it is doing its stuff. So it can do cyclic loading million times without any problem. It can, in compression and tension, it yields, keep yielding, keep moving. So this thing is not connected. So this is one place, this is another one. There is a separation between them. So this is the main part connected to the structure. This is just a casing around that to prevent it from buckling. So it's a simple concept. So these are some of the buildings that we used in the BRBs. You can see here, these are the BRBs. It's real buildings in Philippines. These are the BRBs. So sometimes you put the outriggers like this, not even a line, because depending on how the space is available. So these are all real buildings in Philippines where BRBs, there are two floors are used, one level here, one level here. So these are outrigger BRBs at two levels, and you can see here they're crossing the floors like this. Two floors, not in the same floor, but 2-3 floors, depending upon how much you need. Okay. So that's how the practical application of them, that thing. Now we come to another interesting idea. Once again, as a solution to the architect's problem that they don't want our outriggers to hit the wall. They just don't want that. So engineers come up with the idea of flag wall. Flag wall is the outrigger without reaching the core, kind of a virtual outrigger to some extent, but at the same time not reaching the floor, and it's distributed. So they can be placed wherever the room is available to block some wall and convert that into a structural wall. Okay. So these flag walls are just like flags, like flag posts, flag with the same, they're not connected to the whole thing. They're not beams, but they provide the stiffness. to the floor, the same way that the virtual outrigger does. But they create problems in these areas where they connect because of the local effects and things like that. So we have done several theses on this one. Now this year, another one is going on to study the effect. So these are the flat walls distributed randomly. So these are once again belts or trusses, but they don't go all the way because the architects won't allow all the windows to be blocked or won't allow all the things to be blocked. Even they don't allow belt because there's a window there, you know, CEO's office, they won't want a wall there. So then whatever is left, then that is converted into a wall, and that becomes our flat walls. And then we have to rely on them, the distribution number and so on. So that's the exercise, how many levels, where you place it, and then you try to get, you know, 32 walls, 24 walls, 40 walls. So once again, it's a parametric study. Look at that. So that you compare different systems for their behavior, for drift and floor. So once again, it becomes a research, but then finally you can find a solution that satisfies everyone, architects, engineers, you know, people inside and so on. And this is from that thesis. This is a building without anything. This is one floor of wall, 2 floors, 3 floors, and then 3 floors, 2 locations, and 3 floors, 3 locations. So once again, it's a thesis with all the options studied to find out how a building can be controlled in drift and performance by using the distributed flat wall system. This is another one. So sometimes we use the diagonal one. So another pattern. So this is the normal pattern. This is another pattern. So when we have the thesis, we divided this thesis into 2 parts. One student is working in Manila. One is working in Thailand to study the use of these flat walls in high seismic, high wind zone, and use of these in low seismic, low wind zone. So both of them come up with different solutions. So the same solution won't work in the 2 places. So that's why we studied all these options, because we had a problem in this area with the local effects of the beams connecting there, because suddenly there is a huge transfer of forces from the wall to the beams close to that, and those beams fail because the stiffness changes so rapidly, right? From very large stiffness to just no stiffness. So that's why this is a way to solve that problem, gradually reduce the stiffness, or gradually increase the stiffness. And then another way to do that. So many possibilities are there in flat walls. This is a building, the tallest building in Philippines until recently. And this was the first building that we did. And then here you can see we used the partition walls to actually create a staggered truss system by using the flat walls, but as a truss. So it's a bracing, hidden bracing inside the building, because those walls are placed in a sequence that they also act as a truss, global truss, and also as flat walls. So many, this is the building, the plan over there says, I think 77 stories or something. This is the way it works. So it goes like that. So you can put the flat walls in an outrigger, which goes like this. It completely braces the whole thing. So all we are trying to, in all of these systems, basic intent is the same. We are trying to use the core wall as a central stick and use the columns as vertical elements to support the core wall. That's what we are trying to do. So we're trying to take the bending moment as far away from the core wall as possible to reduce the bending moment on the wall, hence reducing the deformation, hence reducing the drift, and so on. Okay. And this is all real buildings. Look at the flat walls distributed here and there. These are not just ideas from somewhere. These are all actual buildings who have used it and found it to be satisfactory. So this is, once again, you can see here walls distributed here and there, and they help. Another one, similar concept, similar building. Look at the walls distributed here and there, wherever we can find them. And yeah, they're outriggers, they are virtual, they're real, the flag walls, you can call them whatever you like. Right. Now we come to another tubular concept, which was like a revolution for structural engineers when this was introduced. The very first major revolution in structural concept was tubular systems. And this was done a long time ago when the design was done for the Chicago Tower or the Sears Tower, so it was called at that time. And engineer from Bangladesh, Dr. Fazlur Rahman. So he was the one who proposed this system. And he said, why don't we use the outside of the building as a tube and forget about the core wall altogether. Don't try to link the core wall to the frame. Just make the outer skin to take the forces. So the first time we introduce the external system rather than internal system. And then, so basically the way it works is very interesting. So this is a tube, real tube made from concrete wall, right? And now it's interesting. If I take this solid tube and I put some holes in it, it becomes a wall with openings, correct? If I increase the size of the openings, it becomes walls with bigger openings. If I increase the further size, I don't know what this is, but if I increase the size further, it becomes a frame. So basically, it's a smooth transition between a tube and a frame. It all depends on how big is the opening between the beams and between the columns. So if we reduce that opening or we make the columns closer and then keep that opening to a certain minimal size, the ratio of that opening compared to the overall wall, we can achieve the tube effect. Okay. And that was the idea, that we consider the building to be made of a solid tube first, then we puncture hole in it for the windows. So we go the other way. We don't start with the windows and put the columns. We start with a solid wall and then talk to the architect, how many windows do you need? Right? And because at that time, the SOM, the main company, they really wanted to make a very tall building. So they said, okay, we will compromise on the window size as long as you can make this building, right? Because very tall and very, so windows were placed and then, so basically it works on very closely spaced columns and spandrels which are deep. So you cannot have windows like this all the way to you have to have a beam and closely spaced columns. So columns are maybe 3 meters or less, not 7 meters or 8 meters like normal. And the beams have to be large and maybe also at the floor, right? So you get the window in the middle. And as long as that is there, the tube works very well. So then you can optimize the whole system based on the number of, the opening size is the key, like I showed you here. That's how it works. So you basically put the columns, instead of 4 columns, you put 10 columns. And you increase the beam size to reduce and then you get a tube. So then you don't need to connect the core wall to this one because now we are already at the boundary at the outer side. We don't need the core wall anymore. Core wall has nothing to do anymore, right? So we can independently design the building purely on the outer tube. So that is the service core. And normally it's just made from column, not even a wall anymore. In steel buildings, they didn't make a wall. They just make columns also and put the framing on that. Why do you need a wall now? And move the whole system outside. Deep spandrels, closely spaced perimeter, closely spaced columns, and deep spandrels. And that became the tube, and the inner thing, nobody cares about that anymore. So it's a complete reversal of the idea that moved the structure to the skin. And since then, it has become the most common system, especially for very tall buildings. This brings us to the concept of shear lag, our enemy in this case. And we discussed shear lag before. So shear lag basically is that if this was a solid wall, the strain distribution or the stress distribution or the force distribution will be linear from one end to the other. So you can predict the response by that way. And here also, it will be linear, straight like this. So all the columns will work efficiently in that system equally, right? But because of those spandrels, there are beams. So each one is deforming a little bit in shear. So that shear deformation of the spandrels or the beam becomes a shear lag between the two faces now. Because from here to here now, the corner column will get more, and then it will become like this. And here you will lose the effectiveness in the middle. So corner columns tend to get more stress and more force than the one in the middle because of the shear lag effect. At that time, this was seen to be a problem. Now it is seen to be an opportunity to convert the building into mega column. They say, okay, fine. If you don't want, you only the corner columns are working. Why do you have the middle column? Just take them out. So only have 4 columns. So then we moved to another system called mega columns from this one. So somebody saw it as a problem. Somebody saw it as an opportunity. They say, okay, forget about this shear lag business. Just go to mega columns. Get rid of the core. Get rid of the intermediate column. Just have 4 columns on the building. Okay. So anyway, so this shear lag is the main problem in the tubular system, which people have to, do a lot to reduce that effect or to take into consideration that effect. So shear lag effect has to be handled. Okay. Of course, we can reduce the shear lag if you increase the size of the beam, but then the opening side becomes smaller. And so there's a balance between the two. So you can see here that this is the tube. This is 2 pieces. The side walls are connecting them together. This is the opening thing. This is the, so that you can see the main concept. You can use it like this, and like this. Plus, this one, somebody saw this one and said, oh, that's great. This is my Diagrid building. Instead of using column and beam, I will use Diagrid and get rid of the shear lag also. So from this basic concept, many new systems evolved over the years. But at that time, nobody saw them. At that time, people just, and gradually engineers start to take many ideas outside this concept and create new systems. So this is the shear lag effect. I think I don't need to go into detail. I already explained this problem. This also exists in a T-beam. As I told you, when you have a T-beam and a slab, so when you have a deformation in the floor, only part of the slab acts as part of the T-beam at the beam because the rest of the slab is too far. And there is an in-plane deformation of the floor that does not transfer the tension to the compression everywhere equally. So that's why only small portion is part of the T. Same thing goes with the building. Only corners are participating, in between, not so well. So once again, shear lag problem. So as the tube becomes not square, the problem becomes more severe. So square tube is perfect. Circular tube is great. But when you become rectangular, shear lag problem becomes much worse on one direction and the other direction. So it becomes unmanageable, so much so that it loses the tube effect. So this shear lag here, this spindle beam, so the whole thing, you can read about this. I'm sure you will read this. Then frame tube system, write a lot. Please read this. I don't want to. So wide columns, some people use wide columns like this one, still call it a tube, and then take advantage of the core. So people start to combine. If they lose something on the tube, they try to bring in the core. Somebody tried to connect the core to the tube. So use tube plus core plus outrigger. Why not? Right? The basic problem is to make them work efficiently. So people keep doing this kind of stuff. Then architects got more adventurous when they saw this thing. Oh my God, this is great. Then they start to draw all these funny shapes. And then engineers try to fit the tube around those because tubular system seem to work on irregular buildings also, right? Because now there's no problem of the core trying to connect to that. You can just have any shape. So these are the buildings coming up. And then these are the tubes around those. You can see the columns closely spaced. So engineers try to then follow the architects on irregular plans using these irregular tubes. But the problem was stress concentration. Whenever you have irregular stuff, the first thing is stress concentration. So the stresses in the columns were not uniform anymore. They had a lot of discontinuities and stress concentration. But luckily, by that time, we have computers. So now we can do the analysis. We can determine those things. So it start to work fine. But you will see that irregular tubes have a lot of problems. So the continuity of the strain is not like that. This corner, when it comes here, suddenly the tension and compression will change rapidly. It's not a smooth transition like we saw in a rectangular or a square tube. So the stress diagram will be something like this. Now, when we go to the next step, when we do the analysis, you will see that as soon as you put an outrigger in a building, you will have the same kind of issue with the moment and shear plots. suddenly the very nice smooth moment plot and very nice smooth shear plot will be doing something like this close to the outrigger, because the stiffness changes rapidly. So everything changes. So you have large discontinuities close to the outrigger, large stress concentrations close to the outriggers, because stiffness, as soon as its stiffness changes, you get these discontinuities. So that's the problem in all these irregular tubes. Things like this obviously create serious problems. And then people said, okay, fine, if you have a shear-like problem, why do I add diagonals to it now? Right? If I add big diagonals outside on the tube, I will reduce that shear lag, because one of the way to reduce shear lag is to put diagonals. I showed you earlier. We have a shear problem in the frame, you put a diagonal, it stops that from happening. So people started to put those huge diagonals on the building outside. The first one is John Hancock Center, very famous building. And they have once again, the same guy who invented the tube system also put the diagonal in there to solve that problem of the shear lag. So this is that one. So you see here, these tubes, well, and sometimes tube is put by simply putting some of the panels as concrete walls. So just I showed you in the building that we did, similar to that. So very nice, beautiful building, but it's a tube system, diagonally braced to minimize the shear lag effect. So you can see here, engineers have been very innovative in taking the system and modifying it slightly wherever they noticed a problem to come up with a better system. Then we said, okay, core and tube, why don't we now bring two tubes together, one tube inside, one outside, connect them together. So tube in tube concept came up, then bundle tube concept came up. So why don't we have many tubes work together? Now this is the concept for Burj, the Dubai Tower and many other towers, bundle tube concept, right? You put many tubes together and then let them work, and then and then somebody say, okay, I will put them together. I will also put the bracing to solve the problem of the irregular shear flow, right? So sometimes the architect love this kind of thing, so they go with it, and then you get a new, nice, beautiful building. So it's always structural system with the architect, convincing them that it will look nice, right? And express the structural system rather than hide it. So this is the bundle tube system, this one, then you cut the tubes as we go along. So many buildings are of this kind. This is the multi-tube system, many tubes. This is the 4 tubes, then connected together. So buildings of all kinds are coming up. Big, huge towers, especially 4 towers, each in a tube connected together by a huge, floors to make them taller, much taller. This is multi-tube, different configuration of tube. Once again, architects, as you can imagine, it's not engineers' job. They must have come up with these configurations. All of these, multi-tubes, once again, flat slab, look at that. The advantage of all this is that you don't need beams anymore inside. Things that architects just would like to have, no beams, right? And no outriggers, no belts, no nothing. That's the advantage of tubes, that they just convert the facade of the building into the structure. And that also brings us to the same system, very similar, replacing the tubes with the Diagrid. So it's a similar to frames. So basically we convert the square pieces of the window to the diagonals all along, remove all columns, remove all beams, just diagonals, nothing else. So these buildings I've shown you earlier, these so many buildings have come up using this concept, made famous by this building in Gherkin in London. So once this was made, everybody said, oh my God, this is great. So now so many buildings are coming up in that way. I actually joined the presentation by the designer in London when they were presenting this, and he mentioned very clearly at that time that, okay, this building will only work in London. And because, as I mentioned to you, that it's a wind system, it won't work in earthquakes. So when I came back, I gave this project to two students to take that building and try to make it in Manila and see what happens, right? So I'll show you what happened with that idea. So this one is very nice. You can have any form now, and so many forms have been made since then, like this one, all following the same concept. So core versus Diagrid. So this is a core and tube building with beams and columns, and this is the same thing with Diagrid. So again, one of the theses from your seniors who try to compare the same building with tube and same building with Diagrid. How will they work? Frame tube and Diagrid, compare them and take them all the way to design and everything. So this is an interesting study. Again, two theses, one in Philippines, one in Bangkok, same building, and see how it works in both two zones. So this is the steel Diagrid building. Try to do the steel, core and Diagrid combined together and the whole floor. So the whole system is a core plus a steel Diagrid outside. Then you put them together and then you put a floor in between them. So complete the system like that. Floor is not resting, is not rigidly connected to the diagonals. Very important. The diagonal must be free. So you cannot, so the connection between the floor and diagonal has to be a pin. It should not alter the behavior of the diagonal. It cannot be, otherwise the whole system will stop working. So the construction is very, very complicated, because when you bring the floor in, you have to put a kind of a hinge, a floating connection there between the floor and the diagonal. So the diagonal is free to move while supporting the floor also. Sometimes they put the internal hangers to support the floor. So this is Diagrid configuration. So trying different angles, 47 degrees, 65 degrees, 73 degrees. Once again, once you do the research, you can do many things. Whether the Diagrid should be like this or like this or like this, which is most efficient, most economical, right? So you try different angles and then you study them and you find out, okay, which one will work. Only you need, so we found that in Philippines, it didn't work. In Bangkok, it worked beautifully. In Philippines, then we found that the braces or the diagonals at the lower level, even if we make them very big, they would still buckle. They would become just too big and attract more forces. So we decided to replace all the diagonals only in the first 3/4 floors by BRB, first level, 2 levels. So they become like hinge for the whole building to dissipate energy. So the rest of the building becomes elastic and stiff with a hinge at the base, which allows it to rotate and yield during high seismic zone and reduce the forces, of course, because it will yield. But at the same time, it's a BRB, so it won't fail. They think about BRBs, you can't fail it because the mechanism is like this. So you put the BRBs there and the whole building becomes like a nice rigid tube at the base. It just has it will work fine for low earthquake, wind, but as soon as the earthquake is very severe, those BRBs will start to work and they will control the building ductility. Okay, last item, mega frame system. That's what I said that they said, okay, why don't we reduce the number of columns and reduce other columns? So this is the outrigger, and this is a damper put here to control the seismic demand and also put a ductility there, because if you connect this one directly to this one, there's no ductility. So if you want ductility and you want a damping effect, you can put the dampers between these two connections also. So once again, more systems have evolved even with that. And then this is the mega concept, only 4 columns, braced or tubular or whatever you do, or outriggers or belts, whatever you do in between, you just transfer all the forces to 4 columns, completely following the 4 commandments perfectly. There's nothing else. All gravity loads goes to 4 columns. 4 columns act as the lateral system, and they are well connected to each other by braces or by outriggers or belts. So that's the way it works. And these are the examples of that. Only 4 columns you can see here, and then just only go 4 columns going to the base. The rest of the building, look at the diagonals. So I showed you this one. You can do all these things. So these are all real. This has been done. This is a building with just 4 columns with mega trusses, mega columns, and then this one, core inside, not doing anything. So from very simple ideas of the frame, moment frame, people have been evolving the systems to all kinds of configuration. And sometimes it's hard to say, what is this? Because they put everything there. damper is there, the wall is there, the BRB is there, the outrigger is there, the belt is there, the mega column is there. Everything is put in buildings like this. Mega brace is there. Look at once again, mega columns, braces, wall, this one here, outriggers, 8 columns, 4 columns, 6 columns, all configurations. Mostly in China, they are doing a lot of this mega truss, mega column, mega frame system at the moment, because it makes the construction very easy and very fast. Because you just have 4 or 5 or 6 main columns, which they can make very quickly and come back and connect the building. So they just construct them separately and make the building inside later. So it's very fast. So another one here, configuration. This is now 3 mega columns with these braces around that. And then this is important. You should notice this one. The internal columns which are coming to the floor are coming and resting on this one, but they're not going down. So they transfer the load to the mega one, and then new set starts again. So there's a gap. This is very important because these columns are very small, and they must transfer the load to the main columns. One of the commandment, all gravity load must go to the columns which are taking the lateral load. So we don't want these columns to take any load. So every few floors, 10, 15 floors, you transfer them, then start again. Transfer them, start again. So that's the belt truss. Every belt truss is also a transfer girder. So it's doing 2 things. It's transferring the forces of the column above and also acting as a belt truss. Like I said, people just combine things everywhere. So that's another example of the same building. Another one here, exactly 4 columns, bracing, all of that stuff. So this is core, outrigger, this is braced mega tube, this is mixed systems. Everything is possible. Very hard for structural engineers now to figure out which system is the best, because there's so many ways that you can do it, solve the same problem. So very close coordination with the architects, with the contractors, with the construction companies, with the time, with the budget has to be done. It's no longer a simple problem of structural optimization. It's a problem of the whole system working together. Some people say we drive it from the bamboo, which is true, shell thing. Okay, once again, mixed systems, all of that stuff. Okay, spine wall, you've seen that. This is once again, you can see the response, the mega systems, trusses, transfer girders. And this one, a lot.